Hi, everybody. Going to continue talking about radicals today. Last time we were talking about what a radical was, which was an unpaired electron species. Radicals, most of them are highly reactive because they don't have an octet of valence electrons. So they want to desperately complete their octet. They're highly reactive. They're high energy species. And last time we were talking about how their radicals are generated by pumping heat or light into the system, and that causes the breakage of bonds in a homolytic way so that one atom gets one electron in the bond that was ruptured and the other atom gets the other electron in the bond that was ruptured. We also talked about how there are two kinds of radicals. There's the pi accepting radicals. These are resonance stabilized. And then there are the non-pi accepting radicals, and those are not resonance stabilized. So where we left it last time, we were talking about writing resonance structures for radicals. So I want to maybe do one more example about writing resonance structures of radicals. And just to recap what we said about this topic last time, remember that we have two stereotypical moves, which is we have the radical atom is next to a multiple bond. This could be a double bond or a triple bond. And we show the motion of the single electron using these fishhook single-headed arrows. And so we see that in this resonance structure, the dot originally on X has moved over to Z. So that's what resonance is, delocalization of electron density. Okay, the other stereotypical move that we have is that if the radical atom is sitting next to an atom that has an unshared pair of electrons, one of the electrons from the unshared pair looks like it moves over to the atom that used to be the radical atom. So it looks like the dot, the single dot and the double dots change places. Okay, so let's do another practice problem dealing with writing resonance structures for radicals. So if we have, let's try this guy here. Remember, we can either ignore the dot. Oh, the dot should live here. We can either ignore the radical dot completely, or we can move the radical dot around using one of these two stereotypical moves. So we can immediately write a bunch of resonance structures for this radical in which we just ignored the dot and just left the dot be, right? So that could be one resonance structures for the radical. That's just the charge separation of the carbon-oxygen double bond. We've done that a million times. And then we know that this nitrogen atom of this amide has an unshared pair of electrons. We can move him over to come up with yet another resonance structure in which we have ignored the dot. Okay, so we can do this. We can do this as much as we want, just leaving the dot alone and doing something else. But now let's move around the radical dot. Well, I see that this guy here, this is of this type. I see the radical electron is on an atom that is single bonded to an atom which is part of a multiple bond, part of a double bond. So this radical fits in this theme over here. So I can write a radical structure, a resonance form in which I have moved the radical dot, unteaming this double bond. And so I have a new double bond over here. And this nitrogen now has the electron dot on it. Okay, so does that look good? That looks very good. Okay, so now we have to take care of formal charges because remember, without the formal charge, the structure is incorrect. So I see this nitrogen atom here. Nitrogen is group 5. 5 minus 3 bonds is 2. 2 minus 1 unshared electron is positive 1. So this nitrogen has to have a positive charge on it. Well, that just makes sense because this structure is neutral and this one has to be neutral as well. Like we couldn't have just left that negative charge there. Okay, now we can come over here and write some more resonance structures. What I see is that this dot is sitting next to an atom that has unshared pair of electrons on it. So I can formulate my next resonance structure using this this method up here, where the dot and the double bond look like they're just changing places. So now I have a double dot there and a single dot there. And now what about the formal charges? Well, carbon is group 4, 4 minus 3 bonds, because remember there's a hydrogen there, right? I didn't write it. There's 4 minus 3 bonds is 1, 1 minus 2 unshared electrons, that's negative 1. Fluorine is group 7, 7 minus 1 bond is 6, 6 minus 1, 2, 3, 4, 5 unshared electrons is positive 1, so that nitrogen atom has a positive charge on it. Okay, and then let's see. Oh, we can write a bunch of other resonance structures. If we go back to this, let's see. If we go back to, if we go from here, we see that I can write another resonance structure in which I'm ignoring the dot. And now I have a resonance structure. I don't think we've had this one before, no. Ignored the dot. And that would be our next resonance structure. And now I see that this guy is now of the type where I have the dot sitting next to a multiple bond. So this guy is like this. So I can write another resonance structure in which I'm playing around with that dot. So there's yet another resonance structure. So before class, I wrote out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 resonance structures for this radical. I just gave up because, well, I just got bored. So you can write many, many resonance structures for even the simplest radicals. Okay. So now let's get into some of the reactions of radicals. And the reaction we're going to be spending most of our time on is going to be radical halogenation. In which we'll see a CH bond. And this carbon must be sp3 hybridized and never anything else. A CH bond reacts with molecular halogen, right? And in principle, this could be F2, Cl2, Br2, or I2, but it's never going to be F2 and it's never going to be I2. So we're just going to be looking at Br2 and Cl2. And we have heat or light, right? H nu, that's the symbol for light. That's the Planck relation. And what happens is the carbon-hydrogen bond is replaced by a carbon halogen bond. So that's the radical halogenation. Okay, so now before we get into the details of this reaction, let's talk a little bit about why anyone would care. Okay. All right, so this radical halogenation reaction is an important reaction, and a whole lot of stuff is known about this reaction because this is one of the major industrial reactions that petroleum is subjected to, right? Petroleum, the lifeblood of our society. Think about it. You know, I'm here in Massachusetts. I'm here in Boston. Nothing comes from Massachusetts and nothing comes from Boston except maybe college graduates, right? They don't make clothing here. They don't grow food here. It's too cold most of the time. All of the electronics, none of that is made here. Very little comes from Massachusetts. It all has to be trucked in. And how is it trucked in? The internal combustion engine, planes, trains, and cars, right? And where does the gasoline to fuel that internal combustion come from? From petroleum. So petroleum's the lifeblood of our society. But it turns out that another thing that we can do with petroleum is we take the petroleum out of the ground and refine it to a bunch of different compounds, hundreds of compounds that are in petroleum, and then react the petroleum with some kind of halogen. And so there's that radical halogenation reaction where a carbon-hydrogen bond has been replaced by a carbon-chlorine bond. And once the chlorine is on the molecule, and this is something that we'll see next week, once a chlorine atom is on the molecule, that is pure magic. We can do all kinds of things with a haloalkane that we cannot do with an alkane. One of the things that we can do with the haloalkane is swap out the halogen for other functional groups. So what I have here on this slide here is we take the haloalkane that's made by radical halogenation, react it with sodium cyanide, and this would be a way of making a nitrile. So this is how we could change up the functional groups on a molecule. First, radical halogenation of an alkane, and then a reaction in which the halogen is expelled or replaced by another functional group. And then this third line here shows that once we've made the nitrile, we can react that with hydrogen and water and come up with an aldehyde. Okay, so that's why anyone would care about this radical halogenation reaction. It's a way of functionalizing an alkane. It's a way of putting a chemical handle that you can work with on an alkane, and that chemical handle is the halogen. Okay, so here's an example that may be interesting to some of you who are pre-med maybe. So maybe you picture yourself working in an operating room. Well, maybe you're going to use anesthesia. Halothane, this is an anesthetic, a surgical anesthesia. And maybe if you know about anesthesiology, people say, well, the patient is going to get gas. Well, the gas is probably this stuff, halothane. And so we see a sp3 carbon-hydrogen bond that is replaced by radical halogenation to form this halothane itself. But you know what? Radicals aren't just implicated in petroleum and in the chemistry laboratory. Radicals are very hot in the research world right now, because we've said how radicals are high energy, very reactive species. So yeah, there are mechanisms inside your body that create radicals. One of them is oxygen. Well, there's lots of oxygen inside your body. That's what you're using to breathe. And the oxygen reacts with an electron to form this superoxide radical. And this is highly reactive. And so is this hydroxyl radical down here. These are highly reactive species that are formed in physiological systems. And what if these radicals are slamming into your protein and into your DNA? Well, they're going to chemically modify those substances. And the aggregate of this chemical modification by radicals, that is what many people think is actually aging. Right? The burden of radicals have just slammed into your DNA so many times and chemically modified it, and slammed into protein so many times and chemically modified that, and lipids and carbohydrates and everything else. Just the destruction by those very reactive radicals as they bump into biomolecules. That is what leads to aging, some people think. Okay, radical processes are also involved in diseases. For example, this enzyme here, superoxide dismutase, what the job of this guy is to get rid of that superoxide radical, that O2 minus. This is a very destructive radical, so you have a chemical mechanism to defend against the radical destruction. But if you don't have enough superoxide dismutase, if you don't, or if it is defective in some way, if you don't have the enzyme that can take care of these radicals, that is involved. Many people believe in several disease processes. For example, ALS, Lou Gehrig's disease, amyotrophic lateral sclerosis. Right, this is Stephen Hawking here, most famous person, I think, that had this disease, also Lou Gehrig. So radicals, very hot in the research world, figuring out how to minimize the damage that are caused by radicals. Okay, here's our goal. We want to explain the following observations. If you take propane, right, this is just the alkane. This is the molecule that this is a molecule that has sp3 hybridized carbon bonded to hydrogen. That's this guy here. And when we react that with fluorine, and we have heat or light, what we get here is an explosion. Right? We don't get anything useful. We get an explosion, okay? So don't try that at home. Okay, but now if you take this propane and react that with chlorine, right? We've dropped down one notch on the periodic table. Now we get something that is, we don't get an explosion, but what we get is a mixture of products. Right, so what is this reaction doing? It's replacing a carbon hydrogen bond with a carbon chlorine bond. And so this molecule has a carbon hydrogen bond here at carbon 2, and it also has carbon hydrogen bonds at carbon 1 and at carbon 3. So these are just the products of that replacement. And we get HCl as the inorganic junk we really don't care about. And we go into the laboratory and we measure the percent yield of these things, and we see that we get 57% of the 2-chloropropane and 43% of the 1-chloropropane. So this reaction is not useful. When we run a reaction in a laboratory, we want 100% of one thing. We don't want about a 50-50 mix, 50-50 split of two things, right? So I mean, this reaction is kind of a disgrace, because we want 100% of one thing, right? We don't want this split. All right, we drop down one more notch on the periodic table with bromine. And once again, we get replacement of a carbon-hydrogen bond by bromine, and we get HBr as the inorganic junk we don't care about. But in this case, this reaction is much more useful because now we get more than 10 times of the 2-bromo and than we get of the 1-bromo. So now this is workable. This is practical. 92% yield, that's damn good. And the fact that there's more than 10 times of something else, great. That's a useful reaction. Okay, we drop down one more notch on the periodic table. For iodine, same conditions, and what we get here is no reaction. So we've run the gamut, right, from an explosion, a reaction that cannot be controlled, to absolutely nothing happens and everything in between. So what we would like to do is be able to explain this phenomenology. Okay, so let's talk about the mechanism of radical halogenation, how these reactions work. All right, there are radical reactions. They have 3 stages, not steps. It's going to be more than 3 steps, 3 stages, and sometimes many, many, many steps, 3 stages. And the stages are initiation, propagation, and termination. Okay, so let's unpack what is happening in each of these 3 steps. All right. So just to repeat what we said before, is we'll just talk about this reaction. 150 degrees C, we get 2 chloropropane, and we get 1 chloropropane plus HCl, and we get 57% of this and 43% of that. Okay, so just for the record, I rewrote that to just, that's the reaction that we're considering here. Okay, initiation is the first stage of the reaction. And what happens in initiation? The weakest bond breaks. Well, that makes sense because, you know, we're dumping energy into the system. What is going to break fastest? The strongest bond or the weakest bond? It's going to be the weakest bond that breaks first. And usually bonds that don't involve carbon or hydrogen are much stronger than bonds that do, let's say that again, bonds that involve carbon and hydrogen are stronger than bonds that don't involve carbon or hydrogen. So that's just the summary of experience. Lots of times, to help us along, we like to look up the bond energies, the bond strengths. Okay, so now let's look at everything that is present in the system initially, right? Initiation, at the beginning of the reaction. Nothing has happened yet. We're just trying to predict what is going to happen in initiation. Well, we have some chlorine, right? And so the chlorine bond could break homolytically to produce 2 chlorine atoms. And it turns out that I looked up the bond dissociation energy, the bond energy of the chlorine-chlorine bond, and that is worth 243 kilojoule per mole. Okay, so now let's look at some of the bond strengths of some of the other things that are in the system, right? We're thinking about this, the reaction system before anything has happened. And so how about breaking one of the bonds of the alkane to make that alkyl radical plus this hydrogen atom. Well, this bond is worth 423 kilojoules per mole. So it's much stronger. It's not going to be the one that breaks first. All right, another bond that we could consider would be the breaking of this carbon-hydrogen bond here. And I looked up the bond energy of this guy, and this is 403 kilojoules per mole. So it's a much stronger bond than the chlorine-chlorine bond. Okay, so, and there are other possibilities, but we'll just leave it there. So in initiation, the weakest bond breaks. Makes sense. Okay, but one of the things, so this is our initiation step. This is what actually happens in initiation. The weakest bond breaks, and so we've identified the weakest bond. But one of the things that I want to make sure that you understand is that 243 kilojoules per mole of energy, even though that's less than any of these other numbers, is still quite a bit of energy. And it's so much energy, in fact, that the equilibrium constant, remember the equilibrium constant from Gen Chem? The equilibrium constant for the homolytic bond breaking of a chlorine-chlorine bond is, the equilibrium constant here is equal to 3.63 times 10 to the minus 7th, and this is at 150 degrees C. Well, that's a tiny equilibrium constant. What I'm telling you is that tons of Cl2 remain, right? This is a very small equilibrium constant, so that I want to disabuse you of the incorrect notion that all of the Cl2 falls apart in the initiation step. Very little Cl2 falls apart. Lots remain. Why? Because that equilibrium constant is so small. And, you know, in fact, if you want to put a human face on this, right, because this equilibrium constant, this number here, may not mean too much to a lot of people. If we want to put a human face on this and calculate percentages and so on, this equilibrium constant is saying that at equilibrium, there are 1 billion Cl2 molecules left and 13 Cl radicals running around, right? So there's billions of times more Cl2 left in the initiation step than there are Cl radicals. So initiation happens to very few of the Cl2 molecules, but so 13 out of 1 billion. Okay, so that's what happens in initiation. The weakest bond breaks, but please remember that that happens in very few chlorine molecules. There's lots of Cl2 left. Okay, now we're getting to the propagation steps. And there are 2 propagation steps in this reaction. Propagation step number 1, and what is happening here is that those Cl dot radicals, 13 out of 1 billion, they seek to complete their octet. And the way they're going to do that is by slamming into a molecule and robbing an electron and an atom from something. And what is that something going to be? Well, remember, after initiation has happened, we have tons of alkane left that hasn't done anything, and we have tons of Cl2 left. and just very few Cl dot radicals. So the likelihood that Cl dot is going to bump into an alkane is very high because there's tons of alkane available. It hasn't done anything yet. So, but the Cl dot can bump into the alkane in a couple of different ways. So that Cl dot that was formed in initiation can slam into a propane molecule and rob a hydrogen atom from the C1 position. So if we want to show the movement of those annoying fishhook arrows, we would be saying that the Cl dot slams into this molecule and it unteams that carbon-hydrogen bond. We have this primary radical that is formed plus HCl. Okay, now we go back to the bond dissociation energy table and we can put this on a quantitative footing. This bond is worth 423 kilojoule per mole. The bond that was formed in this reaction is worth 431 kilojoules per mole. So we can calculate the delta H, we can calculate the energy of this reaction. So the delta H standard, right, is going to equal the sum of the bonds broken minus the sum of the bonds that are formed. All right, and so now this makes sense because bond breaking is endothermic, right? Is that you have to put heat or energy into the system to get that bond to break. So these numbers are going to enter in as positive numbers. Bond formation is exothermic. Heat leaves the system. So these numbers are going to come in as negative numbers. Okay, so who was the bond that was broken? 423. Who is the bond that was formed? 431. Total -8 kilojoules per mole. Okay, so that's one thing. That's one thing that could happen, but it's not the only thing that can happen. Chlorine could slam into propane in such a way to rob the hydrogen atom on carbon 2, resulting in this secondary radical plus HCl. Okay, and once again, we go to our table of bond energies and we see that this bond is worth 403 kilojoules. The bond that was formed is worth 431. So the delta H of this reaction is going to be bonds broken minus bond formed. And this is working out to -28 kilojoules per mole. Oh, okay, that's more favorable, right? Both of these are downhill in energy, but we're starting to get the suspicion that this step would be more favorable. Okay, so this is what, both of these guys happen, right? Both of these steps happen. It's not going to be just the one that is the most negative one. Both of them happened, and the reason we know that is we get about a 50-50 mixture of products where the Cl ended up on carbon 1 and where the Cl ended up on carbon 2. All right, I want to take a little pause from this to just consider these bond dissociation numbers a little bit more carefully. We're going to continue with propagation, but let's just take a little break to talk about those bond dissociation energies. Bond dissociation energies. All right, and so this is abbreviated BDE. Also, you see in some textbooks something that's called DH standard. Okay, so this is the amount of energy. This is the amount of energy needed to break a bond homolytically. In other words, the bond is broken and one atom gets the dot and the other atom gets the other dot. And when we look at some bond dissociation, when we look at the bond dissociation energies that we've considered up to now for these organic radicals, we saw that this guy to make this radical here plus a hydrogen atom, we saw that this guy was worth 423, whereas this bond dissociation energy, this was worth 403. Okay, and we see that it takes more energy to break the C1 hydrogen bond than it takes to break the C2 hydrogen bond. The interpretation of these numbers is the following. More energy needed. Why? Because this radical is less stable. This radical doesn't want to form. Less energy needed here. Why? Because this radical is more stable. It forms more readily. That's why less energy is needed. So that's the interpretation of these numbers. A bigger BDE, that means a less stable radical. Doesn't want to form. That's why you need so much energy. A smaller BDE, that means a more stable radical. It forms more readily. So by looking at a table of bond dissociation energies, hope I have one. Aha. By looking at a table of bond dissociation energies, I can identify trends in radical stability. Okay, so trends in radical stability. All right, so if I look at methane, right, and this bond breaks homolytically to make the methyl radical and a hydrogen atom, this bond is worth 437. Okay, so I'm replacing one of the hydrogens in methane with a methyl group, and I'm going to get hydrogen atom, and this guy, this bond is worth 419. So that's a little bit less. This radical, this ethyl radical, is more stable than this methyl radical by about 20 kilojoules per mole. And now when I replace another hydrogen with another methyl group and look up the bond dissociation energy there, Okay, so this one, that's that 403 that we've made several references to already. Okay, and then I'm going to continue and conclude my table over here. And now if I replace the final hydrogen with another methyl group, and so I'm going to get this radical here, plus H dot, and this bond dissociation energy here, this is worth 392. These numbers, these BDEs are going down. How do we interpret that? The stability of these radicals is going up. This radical forms more readily than that. Okay, so let's do some more exploration of the bond dissociation energy table. And for example, something like this, where I'm replacing now this is going to give me a pi accepting resonance stabilized radical. And the BDE of this guy is 375. Oh, it's even more stable. This radical, because it's pi accepting and resonance stabilized, is even more stable than this one. Okay, but what happens if I try to replace a hydrogen that is not on an sp3 hybridized carbon? What happens if I try to break a bond, a carbon-hydrogen bond that isn't to an sp3 hybridized carbon? sp3 hybridized, sp3, 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 sp3. Now let's look at a situation where I'm going to replace I'm going to form a radical by breaking an sp2 carbon hydrogen bond. Look up the bond energy here. Oh my God, 473. That's even worse than this, right? So this is an extremely unstable radical. It takes a whole lot of energy to get it to form. And so that's why this bond dissociation energy is so high. We would like to understand these trends, but before we get to the explanation, let's just let's summarize the results. The most stable kinds of radicals are the resonance stabilized types of radicals. The radicals for which we can draw resonance structures, the pi accepting radicals. And then a tertiary radical, then a secondary radical, then a primary radical, and then a superprimary or methyl radical is the least stable of all. Okay, so this methyl radical, this is considered superprimary because the radical carbon is bonded to 0 other carbons. This radical is a primary radical because the radical carbon is bonded to 1 other carbon. This is a secondary radical. This is a tertiary radical. This guy would be called a resonance stabilized, abbreviating everything here, resonance stabilized primary radical. Okay, so this is the trend that we observe phenomenologically. This is what we see in the laboratory. Now let's talk about the explanation. Is that radicals are stabilized by what is called sigma donation. Remember, we were talking about how a radical that is not pi accepting, for example, the methyl radical, is tetrahedral. It looks like this. Versus, let's look at a primary radical, right? That's super primary. Let's look at a primary radical where we're going to replace one of those hydrogens with an alkyl group. Now, this bond, it's really an orbital. It's really an orbital. And what is thought to be happening here is that this, the radical carbon that doesn't have an octet, that is dying to complete its octet, is stabilized by an orbital on a neighboring alkyl group. This orbital senses the electron deficiency here. Lots of electrons here, not as many electrons here. And so these electrons feed the radical dot, this radical carbon. Well, the reason the radical is unstable to begin with is because it is missing electron density. It doesn't have an octet. It only has a septet. So what a neighboring alkyl group is doing is it is decreasing the electron deficiency of the radical. The radical is unstable because it's missing electrons, but a neighboring carbon-hydrogen bond can pump electrons into that radical orbital, and now the electron deficiency has been decreased to an extent. And now when we load up the radical with even more alkyl group, maybe put one on one side, put one on one side, and put one on the other side. Now this radical is being helped by two orbitals on adjacent carbons. And so this is why we believe that a superprimary radical is less stable than a primary, which is less stable than a secondary, because the neighboring orbitals are contributing to its electron, are decreasing its electron density. Oh, and resonance, that's a much more powerful effect, because there we have the wholesale transfer of electron density from the stabilizing group to the radical atom. Okay, so we've just explained how resonance stabilized radicals are most stable, then tertiary, secondary, and then primary. Okay, so back to propagation. All right, so propagation step number 2. Propagation step number 2. And what is going to happen in propagation step number 2 is that in propagation step number 2, now the radicals that were formed in propagation step number 1, they seek to complete their octet by bumping into something of which there is a lot of in the reaction mixture. So one of the radicals that was formed in propagation step number 2 was this primary radical. He is going to slam into Cl2. Remember, we said there's tons of Cl2 left. Initiation doesn't kill all of the Cl2 molecules. It will only kill 9 in a billion of them. There's tons of Cl2 left. And so this radical slams into Cl2. And what it is going to do is it's going to abstract a chlorine atom with the fish hooks once again. It's going to abstract the chlorine atom. And there's our product. This is the one that was formed in 57% yield. Can I repeat what? The definition of what? So at the end of propagation step number 1, we formed some of this radical. We have lots and lots of Cl2 remaining. This radical is seeking to complete its octet, and it is going to do so by by reacting with Cl2, and it's going to abstract, it's going to remove a chlorine atom from Cl2. The other product of this reaction would be Cl dot. Okay, so now let's do some numerology here. The chlorine-chlorine bond is pretty weak. That's 243 kilojoules per mole. And this bond, this was formed, that's 354 kilojoules per mole. So the delta H of this step is minus 111. Wow, that is huge downhill in energy. Okay, but at propagation step number 1, we also had this secondary radical was formed. And so he's going to complete his octet by reacting with Cl2, and we get the Cl in that carbon 2 position and more Cl dot. Okay, so now the numerology for this step would be 243 for Cl2, and this is the bond that was created. This is worth 354. We do, yeah, not a mistake. These are the same numbers. And so conveniently, this is also equal to minus 111 kilojoules per mole. Okay, so couple of observations about the propagation steps is that the propagation steps sum to the overall reaction. Okay, so what did we write for propagation steps? We wrote this guy plus Cl dot makes this guy plus HCl. That was propagation step number 1. And then propagation step number 2 for this system would be that radical plus Cl2 makes the 1-chloropropane plus Cl dot, sum. This guy cancels this guy, Cl dot cancels Cl dot, and what is left is the overall reaction with the reactants on the appropriate sides of the arrow, right? And we could also do this very same summation for the 2 propagation steps that led to the 2-chloropropane. That's one observation about the propagation steps. They add up to the overall reaction. Another observation about the propagation steps is that the propagation results in the formation of a self-sustaining chain reaction. All right, and so this is a subtle point. See, way back here when we're talking about initiation, made the point countless times already that only 13 Cl dots are created for every billion Cl2s that absolutely nothing happened to. But when we look at the propagation steps, we see that the propagation steps create more Cl2, but not in an initiation step. The reaction needs Cl dot. I may have said that wrong. The propagation steps create more Cl dot. The reaction needs Cl dot to get going. Initiation provided a very few Cl dots, but once the propagation steps take over, now it's a runaway chain reaction because the Cl dot that is needed to get the reaction going is created by the propagation steps. That's why initiation doesn't have to happen to every single Cl2 molecule. That's why only 13 in a billion have to react, because when propagation begins, propagation is going to create more Cl dot. Okay, so now before I take my break to go have some coffee, let's just talk about termination. What happens in termination is that two radicals formed in propagation collide to form a non-radical species. Okay, so if we look back at the propagation steps, we saw that Cl dot is involved in propagation. A Cl dot could collide with another Cl dot to make Cl2. That's a termination step, is that the chlorine radical wants to complete its octet. Both of them do. They're going to do that by combining. Termination only happens at the end of the reaction. That's why it's called termination. This is happening at the end of the reaction when propagation has pretty much run its course. The likelihood of two Cl dots bumping into each other at the beginning of the reaction is very low, right? Because we only have 13 out of a billion. So this is not likely to happen at all at the beginning of the reaction, but near the end of the reaction, now the likelihood that these two radicals could collide is much higher. Cl dot could also bump into this primary radical to make something that looks like the product. And once again, the likelihood that two radicals find each other, that is very low as long as propagation is happening. Propagation is all about a radical bumping into something that is not a radical. Propagation is all about something that a very low concentration bumping into something that is very high concentration. But what happens when all of the reactants are nearly used up? Now these reactions become competitive. Another thing that could happen is that this primary radical could collide with another radical that's just like it, right? To form something, the electrons team up and you get this 1, 2, 3, 4, 5, 6, you get this hexane. That's another termination step. But remember, these termination steps are of very little importance while propagation is going on, and and these reactions are only important at the near the end of the reaction. Okay, so I'm going to take a break now. Go have some coffee. My clock says 10:01, so I'll be back at about 10:10. Okay, so we've gone through a bunch of numerology for chlorination. Now, I'm not going to present all of those explicit details for bromination, but it would be the same kind of calculation, is that we're looking at the two propagation steps and we can calculate the delta H of each step. It's the bonds broken minus the bonds formed. Okay, so let's do chlorination versus bromination. Because remember, what we're trying to understand is that the chlorination gives us about a 50-50 mixture of two products, but bromination, we get 10 times more of one product than of the other. Okay, so just for the record, just looking at the two propagation steps, we had this guy plus Cl dot going to primary radical plus HCl. And what was the delta H of this step? -8 kilojoule per mole. Okay, we also had this step. Do I want to do it that way? No. Now, if we used Br2 instead of Cl2, the first propagation step would be the same, except here we're getting HBr instead of HCl. And the delta H of this step would be positive 57 kilojoules per mole, right? So that was propagation step. That was propagation step number 1, right? Okay, so now if we look at propagation step number for this other guy, plus Cl dot going to secondary radical plus HCl. What did we get for this? -28. But now when we swap out Br2 for Cl2 and we swap out bromine radical for chlorine radical, this step is now positive 37. Okay, so these are all propagation steps number 1, but remember we're getting different products. Okay, so now just for the record, just so that we have all of these numbers available, right? Let's look at the propagation step number 2. It's going to be this organic radical plus Cl2 to make the 1-chloropropane plus some chain carrying self-sustaining Cl dot. And what did we calculate for this? This was -111 kilojoules per mole. And now when we swap out the Cl2 for Br2, we're going to get the 1-bromopropane plus chain carrying Br dot. And this one is worth minus 71. Where am I coming up with these numbers? I'm just doing that bond energy calculation. Okay, so that's propagation step number 2, leading to the 1-halo compound. And then we have propagation steps that lead to the 2-halo compound. So we did this one, and what did we get for that? Minus 111. Oh yeah, it was the same as the other one. And when we swap out Cl2 for Br2, we get the 2-bromopropane plus chain carrying Br dot. And this works out to minus 106. So that's propagation step number 2 for the second product. Okay, so now, so let's just keep these numbers just handy. And now what we want to do is we want to plot all of these on an energy diagram. And at the end of this, we'll see why we get so much more of one bromination product than we get of the other. Okay, so on our energy diagram that we're going to cook up here, I wrote this out before class, so I don't want to make an ugly drawing here. The horizontal axis, that's going to be delta H. That's going to be the energy. And the x-axis here, this is called the reaction coordinate. This is not something new. We saw something like this when we were talking about the Newman projection and the rotation of the carbon-carbon single bond. In the energy diagram that we came up in that instance, the x-axis, that was also a reaction coordinate. It's a geometrical coordinate. It's not time. It's a geometrical coordinate that represents the extent of bond making and bond breaking. Okay, so what I'm going to do is I'm going to put the in the system here, sort of in the center. All right, and so this is the initial state of affairs in which I have Cl2, I have propane, and I have that initiator radical Cl dot, right? That's at the start of the reaction. And then propagation step number 1, I'm going to go down by 8 kilojoules per mole. I'm going down by 8 kilojoules per mole. To make this primary radical plus HCl plus Cl2, because remember there's a lot of Cl2 still left in the reaction mixture. And then propagation step number 2 for this guy. So I'm here now, and I'm going to drop down 111 kilojoules per mole. So that's going to be way down here somewhere. All right, and so there's our product. plus HCl plus more chain carrying radical. Okay, so this would be, that's the 8. And this is the 111. Right? And I'm going down because all of these numbers were negative. Okay, so now I'm going to, on this already very crowded diagram, I'm going to plot what is going to happen when I'm creating that secondary radical, but I'm going to do that on this, on the other side over here. Okay, so let me see, let me get my data. All right, so to make this product where I made the secondary radical, I'm going down 28. So I'm going to put that down here somewhere. So if that was 8, maybe 28 can be here. To make that secondary radical plus HCl plus Cl2, right? And so this distance here, that's the 28. And then I'm going to go down for the second propagation step. I'm going to go down, where was it? Oh, that's that 111 again. So now I'm going to go down 111. It's going to be way down here somewhere. That's the 111 down to here, where I get this 2 halo plus HCl plus Cl dot. Whew. Okay, so I hope you could see what I'm trying to do here is that when I mix Cl2 and propane and some initiator radical, 2 things happen. One thing is the formation of the 1-chloropropane, right? And this would be, what was that in 50? That's the 47% yield guy. And the other thing that happens is formation of the 2-chloropropane. That's going to be in that 57% yield, right? So I'm starting here and the reaction goes either to form the 1-chloro or the 2-chloro. That's what I'm trying to express here. But all of this numerology, all of these numbers is just telling me where the energy level of the reactant and the product is. Now what I need is something, I need to connect all of these states with a nice smooth curve, just like we did it with the Newman projection. But in the Newman projection, I could calculate the energy of the transition state, and that was telling me how high the hill is. Here, I don't have that. Instead, what I have to guide my pen, instead what I have here to tell me how big to make the hill is the Hammond postulate. And so this was a proposition postulate. This was a proposition that was cooked up by Professor George S. Hammond of Caltech. And this is what I'm going to use to guide my pen. This is what is going to tell me how big or how small to make those hills. First of all, some vocabulary. What is a postulate? A postulate is a working assumption. You assume it to be true, and then you have to go out into the laboratory and verify whether that assumption was justified. That's what a postulate is. I could make the postulate that everybody loves chocolate. That may or may not be true. I'd have to go out and ask 100 people, do you like chocolate? But that would be my working assumption, my postulate, everybody loves chocolate. Well, here, what the Hammond postulate is saying, the working assumption is that if delta H dagger is less than 0, if it's negative, the activation enthalpy is small. And if delta H0 is positive, the delta H dagger is big. Well, that kind of makes sense, that if the energy, if the overall energy change of a reaction is very favorable, if it's way downhill in energy, then what Hammond's postulate is assuming is that the rate of the reaction, the hill that separates the reactant from the product of that reaction, is going to be small. All right, so this is the guide for my pen. I'm about to connect everything with a nice smooth curve, and I'm going to see, and I'm using the Hammond postulate to guide my pen. So this was down by 8. I'm going to make that hill small, right? I'm not going to go way the heck up here and then down. Oh no, what I'm going to do is I'm going to make that a very small hill. Okay, so this next step was down 111 kilojoules. That's going to be even, that's even more of a drop. So maybe this hill is even smaller. So I'm going to make this very small hill like that. Okay, so now what about in the opposite direction? This is this is the profile to make the 1-chloropropane. What about the profile to make the 2-chloropropane? Well, I got a drop of 28. So I'm going to make that a very small hill. And now I got a drop of 111. I'm going to make that a very small hill. So that would be my energy diagram for chlorination of propane. And this is explaining why it is that I get about a 50-50 mixture of chlorination products, because the energy barrier to form the 1-chloropropane is about the same as the energy barrier to form the 2-chloropropane. Right, the hill in this direction is about the same size as the hill in this direction, so that the system doesn't really care whether it forms the 1-chloro or the 2-chloropropane. Which is the faster reaction? Well, this one is, but not by much. This hill is tiny. This hill is tiny. That is what the Hammond postulate is saying. So we see now why chlorination replaces hydrogens with little selectivity, with little preference, because the replacement of a primary hydrogen and replacement of a secondary hydrogen, they happen at about the same rate, because the energy barrier for both processes is about the same. Okay, now we have to repeat all of this again, but this time for chlorination. All right, so let's make our energy diagram, this time for bromination, I mean. So let's make our energy diagram for bromination. And so this would be those H standards, and this would be the reaction coordinate. And once RXN means reaction. And once again, I'm going to start things off. I'm going to put everything here in the center. I'll put everything here in the center. And who lives here? The propane, the Br2, and some initiator radical. And now to the left of this diagram, I'm going to put the 1-bromo propane numbers. All right, for that first propagation step, I got plus 57. So I'm going up. I'm going up by 57. And who lives here? The primary radical plus HBr. plus Br2. And then in the second propagation step, where are my numbers? Second propagation step, I'm going to go down by 71. Right, so this distance here, that was the 57. Now I'm going to go down by 71, down to here. That's going to be the 71. And here I have my 1 bromopropane plus HBr plus Br dot. Okay, so now let's go to the right, where we're going to plot all of the numerology for the 2-bromopropane. Okay, so first propagation step, that was up 37. So that's the 37. And who lives here? The secondary radical plus HBr plus Br2. And then I'm going to go down 106 in the second propagation step. So I'm going down 106. So that's going to be maybe down here somewhere. Obviously not to scale. So now I'm going to go down 106. And there's my 2-bromopropane plus my HBr plus chain carrying Br dot radical. Okay, so now I'm ready to connect everything with a nice smooth curve using the Hammond postulate, which is saying that if the reaction is uphill in energy, that is going to be a big activation barrier. That's going to be a big hill. So this is quite uphill. This is quite uphill in energy. Look how big that hill is, right? But this isn't as far uphill in energy. So the activation barrier is going to be just like that. Okay, so now this is way downhill in energy. That's going to be a small hill. And this is way downhill in energy. That's going to be a small hill as well. So that's my reaction profile for bromination. And now it is clear. Now it is clear why I get 92% of this guy and only 8% of this one. Because the reaction starts here and it has two options. It can either form the 1-bromopropane or it can form the 2-bromopropane, but the activation energy leading to the 2-bromopropane is much smaller than the activation energy leading to the 1-bromopropane. This hill going to 1-bromopropane is much tougher to overcome than this smaller hill over here. So the reason that bromination and chlorination give such different product distributions is because that first propagation step is has about the same activation barrier in chlorination, but for bromination, it's very, very different. All right. So that has explained a lot, right? So now let's look at some practical applications of these reactions. And that is, let's just do a summary of what we said. Cl2 replaces hydrogens with little preference. The energy barrier for that first propagation step, no matter what Cl replaces, is going to be about the same. But Br2 replaces the hydrogen that gives the more stable radical. Doesn't have two L's. More stable radical, preferentially. Right, that's what's happening here, is that the 92% product came from the secondary radical, which is more stable than the primary radical. Okay, so we can use this for product prediction. So for example, if I were to have this guy, and if I were to react him with Cl2 and heat, what would happen? Well, Cl2 replaces hydrogens with little preference. So what I'm going to get is replacement of this hydrogen over here to give that, plus the replacement of this hydrogen down here to give that, plus the replacement of the hydrogens that live here to give that, plus the replacement of this hydrogen over here to give that. The reaction is a mess, right? Because Cl2 is not selective. I get all of these products. But when I react that very same alkane with Br2, I see that if I put a dot here, that's going to be a primary radical. That's going to be a primary radical. If I put the dot here, there's a hydrogen there. This hydrogen is replaced. That's going to give me a tertiary radical, secondary radical, primary radical over here. I'm going to get probably an overwhelming amount of that as the major product by a lot. Right, so chlorination is not useful unless there's only one possible product. Bromination is much more useful because bromination is going to replace a specific hydrogen, the hydrogen whose removal leads to the more stable radical. Okay, so let's try another product prediction problem here. Let's see, I think I have a slide here. Yeah, right there. Draw the structure of the product. I've even given you the NMR. Okay, so you work on that for a while and you tell me what the structure of the product is. What are we talking about? We're talking about how Cl2 replaces hydrogens with little preference. We're talking about how Br2 is going to replace the hydrogen whose removal leads to the more stable radical. All right, so that's the major product. There's the formula, there's the NMR. Don't really need the NMR to figure out what's going to happen, but just thought I'd give it to you anyway. Okay. So got to kill this. Tell me in the chat, what's the product? Which hydrogen? Let's see, why is this? Why can't I move my chat window? Yeah, tell me here in the chat, which hydrogen is going to be replaced, right? Here's the problem right here. Draw the structure of the product. Tell me in the chat. Would it replace one of the hydrogens on the benzene ring? Well, it would not. Because when we started talking about this reaction in the first place, I made the point that the hydrogen that is replaced must be on an sp3 hybridized carbon. A hydrogen on the benzene ring would not be replaced. And I also said, and I gave you some data, I also said that the radical where we replaced a hydrogen on a benzene ring is hugely unstable, right? So let's try again. Would it replace a hydrogen on the benzene ring? It would not. Anybody want to give it a shot? Draw the structure of the major product. Anybody out there? Oh, maybe someone had an answer. Okay, next guess would be one of the CH2, one of the hydrogens on the CH2. Yeah, but I see two CH2s, so which one is going to be replaced? It's going to be this one, via this resonance stabilized radical, right? Because Br is replacing the hydrogen that gives the most stable radical. If I put the radical dot here, I get a resonance stabilized radical, and it's also secondary resonance stabilized. If I put the dot over here, that's just a secondary radical, not a stable. If I put the radical dot over here, I'm going to get a primary radical. That's one of the worst kinds of radicals, right? So the product here is going to be replacement of the most of the hydrogen that leads to the most stable radical. And when we look at the NMR, let's go back to the NMR here. We see there's 3 hydrogen, that's the 3 hydrogen doublet, 3 hydrogen triplet, that's next to a CH2. Okay, these are all of the benzene ring protons over here, 5 hydrogen, and this is a quintet. This is a quintet. It's something that is split by 4 protons, and there's a triplet. Okay, that did not go well. Let's try another one. Br2 and heat. Draw the structure of the major product. So if you want to be really good, instead of telling me the one closer to the benzene, because here there is no benzene. If you want to be really good, how about trying to cook up the name of the compound, right? We spent all that time with nomenclature. The reason we spent all that time with nomenclature so that you didn't have to tell me, well, it's the one next to the benzene ring. right? And there is no benzene. Okay, tell me in the chat what's going to be, where's the BR going to end up? One methyl, one bromocyclohexane. Thank you. Yeah, the product is going to be this. Because what has happened is that bromine replaces the hydrogen, whose removal results in the most stable radical, right? So if I put the radical dot there, I get tertiary. If I put the radical dot over here, I get primary. That's terrible. If I put it here, that's secondary, that's secondary, that's secondary, that's secondary, that's secondary. The radical bromination mechanism operates by forming the most stable radical possible in that first propagation step. And here, there's the tertiary will be more stable than anything else. Yes? Okay, so that didn't go too well either. Let's try again. Okay, here I don't expect you to cook up the name. Just tell me in the chat in words, where's the new bromine? Anybody want to give it a shot? Could it be on either of the shared carbons? Yes, where the two rings connect. Yes. Okay, now it looks like we're getting somewhere. Yeah, that's going to be the major product. I could have also put the BR down here at 6 o'clock. It's the same thing. It's just it's just like the rotation, the C2 axis rotation. Via a tertiary radical. If I put the radical dot anywhere else, it's going to not be as good as tertiary. It's going to be a secondary radical. Versus what would happen if I were to take this methyl cyclohexane and react it with chlorine, right? I'm going to get a mess because chlorine replaces hydrogens with little preference. So I'm going to get substitution here, there, etc. Lots and lots of different chlorination products because chlorination doesn't care about radical stability. Bromination does. Okay, so chlorination versus bromination, we get some very different products. All of this can be put on a quantitative footing, on an even more quantitative footing. That's what I want to talk about now. A whole lot is known about these reactions because, as I said, petroleum is the lifeblood of our society, and a whole lot is known about the chemistry of petroleum. And one of the things that the petroleum is used for is to create new molecules, plastics, all kinds of stuff from petroleum. And one of the steps is going to be chlorination or bromination or something like that. So a whole lot is known about this. And in fact, we can even predict the percent yield of each product. So that's what I want to talk about now. Okay, so this is, so for replacement of a primary for replacement of a hydrogen on a primary carbon, Cl and Br, the relative reactivity, just going to call that 1. For replacement of a secondary, of a hydrogen on a secondary carbon, for chlorine, relative reactivity 4.4, relative reactivity for bromine is about 80. See how chlorine doesn't really care about radical stability, but bromine does, and we went through all of that from the shape of those curves. For replacement tertiary chlorine, it's about 7.2. There's not a whole hell of a lot of difference between 1 and 7.2 when you compare that to the bromine number, which is 1700. So what are these numbers here? These are relative reactivities. But now we have a complicating factor in that we have a statistical factor. Okay, so for example, if we have something like this, and we react that with Cl2, we see that we can replace any of these carbons. We can replace these we can replace the hydrogens that live on these carbons with Cl, and we'll get maybe something that looks like that. But if we replace one of these hydrogens up here, we get the same thing. If we replace one of these hydrogens here, we get the same thing. So this molecule has 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens that are chemically equivalent by symmetry and by a rapid mechanism, right? The 3 carbons of a methyl group are all, the 3 hydrogens of a methyl group are all equivalent to each other. And here, this molecule would give 2 NMR signals, one of them for these 9 methyl protons, and one of them for the hydrogen that lives there. So there are the 2 products, but we have to take into account a statistical factor. So this is a primary replacement, but there are 9 equivalent hydrogens that can be replaced to give this very same product. So it will be the relative reactivity times a statistical factor. This guy over here, it will be the relative reactivity (7.2), replacement of a tertiary, times a statistical factor. There's only 1 such proton. Okay, so this worked out to 9, and this worked out to 7.2, correct? Okay, now, the percentage of this guy here is going to be the 9 divided by the 9 plus 7.2. The percentage of this guy is going to be the 7.2 divided by the 9 plus 7.2. Someone there with a calculator? I didn't bring mine. Can someone give me these numbers? Can someone calculate these numbers and tell me what I'm getting? Please. 9 divided by 9. 55 and 45. Thank you. 55% and 45%. Right, so Cl2 replaces hydrogens with little preference. Okay, but now when we do this very same experiment, with Br2, let's see what we're going to get. Okay, so we're going to get this plus this. Okay, so the statistical factor here, that's a primary, that's a 1. That's the reactivity factor, times the statistical factor, which is a 9, that's a 9. Here we have a reactivity factor of 1700, because that's tertiary, times the statistical factor that there's only 1. That's going to be 1700, that's going to be 9. Well, I don't need a calculator, but this is probably, maybe some of you who have a calculator, maybe you could tell me, isn't this going to be 99%? Anyone with a calculator out there? Yeah, this is 99.5%, and this is 0.5%. Right, huge difference, because bromine is so much more selective because it is going through the most stable radicals. So get my head out of the way. So we can predict using these, the type of hydrogen being replaced and the statistical factor and the reactivity factor, we can predict the percentage of each product that is formed. Okay, so I'm going to stop there.